So now we've started to look at how we can improve some existing tools that we've had in our toolkit to study inorganic complexes. When we looked at IR spectroscopy, we were looking at how we can use these molecular vibrations to characterize different geometric isomers of transition metal complexes, as well as predict the entirety of the IR spectrum, right? The total number of signals that we had. So if we go back a few lectures to our ligand field theory discussion, where we saw that depending on the ligand types that were bound to a complex, whether we had pi donors or sigma donors or pi acceptors, we see this difference in this value of delta octahedral, right? This energy difference between our lower lying T2G state and our higher lying EG state. And so if we want to measure this value, if we're looking at the difference between these ligands in our spectrochemical series, we want a way to actually study and derive a numerical value for delta octahedral. So if this is the difference between orbital energies, right, if we're looking at the difference between electronic states, we might think about using absorbance spectroscopy. And so if we go back to general chemistry, Chem 124, right, we said that these electronic transitions were something that we can study using absorbance spectroscopy. One of the things that many of you have talked about for inorganic chemistry and have heard about inorganic chemistry is that our compounds are brightly colored, right? That's one of the selling points of this subdiscipline. And where these bright colors come from is actually absorbances in the visible region of the electromagnetic spectrum. And so we might imagine our simplest case for our electronic transition, right, being a D1 metal. So if we just had a single electron, right, in our D electron count, we could imagine that if this is sitting in the T2G orbital set in its ground state, we imagine an excited state that has that electron in one of those EG orbitals. And this electronic transition seems like it should correspond in energy to delta octahedral. And in fact, let's say, for example, we look at a titanium 3 plus case and we look at the absorbance spectrum. We do, in fact, see one principal absorbance in the titanium 3 absorbance spectrum. So this peak here at about 520 nanometers under these different conditions corresponds to that D to D transition, right? That T2G to EG transition in our metal complex. We notice here that our y-axis is actually using the values of epsilon, the molar absorptivity constant, and not directly absorbance. This goes back to the molar absorptivity constant as being, again, a constant at a given wavelength. And as long as we know our concentration of our sample, we can convert to this value of epsilon. And this is an important feature of the spectrum, as we can see that we have a higher peak, right? One that has a greater value in this molar absorptivity constant, and one that has a smaller value, right? For one set of these conditions, right? From this plot here. And so what is it that epsilon actually tells us about our electronic transitions? Up until now, all we've really focused on was lambda. And yet this value of epsilon is important, and it tells us something about the nature of this electronic transition. So what does it tell us? Well, in order to understand this, we have to understand our two selection rules for electronic transitions, right? And these two selection rules are something we're going to come back to throughout this unit. And so the first is what we call our spin selection rule. And what this spin selection rule states is that electronic transitions between states of the same spin multiplicity are allowed. And this spin multiplicity, we've talked about this a time or two in the past, is just a description of our overall spin state for our complex. And so this has the equation that this m sub s is equal to 2s plus 1, where s is the total of our electron spin for our system. And so what our spin selection rule is saying is that if we do not have any change in our spin multiplicity, that would be considered a spin allowed transition. So for example, if both our ground state was a singlet and our excited state was a singlet, meaning there are no unpaired electrons, right? That capital S is equal to 0 in this case, then we would call that a spin allowed transition. However, if we do see a change in our spin multiplicity, we would call that a spin forbidden transition. So if we go from a singlet to a triplet electronic state, that would be a spin forbidden transition. And so this is why whenever you see those excitations drawn within orbital diagrams, you don't generally flip the arrow once it's in that higher energy state. in order to account for these spin-allowed transitions. Our second selection rule is what we call the Laporte selection rule, also known as the parity selection rule. And this states that electronic transitions between orbitals of the same parity, that is, orbitals that have the same symmetry with respect to inversion, are actually forbidden transitions. So if we're looking at an orbital transition that goes from U to G, right, the subscript label U and G has to do with the symmetry with respect to inversion. If that label changes, it's what's called a parity allowed transition. However, if that label stays the same, it's a parity forbidden transition. And when we're looking at this very bottom example, you might notice why this is a problem for inorganic chemistry. If we go back to our ligand field for an octahedral complex, we're looking at a T2G to an EG transition. So these are actually parity forbidden transitions. Now, forbidden is actually a bit of an intense word. Instead of forbidden, you could think of these as weak or poor or unlikely transitions. It doesn't mean that they don't happen. It means that a special set of conditions has to arise in order for them to be observed. One of these special sets of conditions could simply be molecular vibrations and torsional twists of our complexes. So essentially, we can momentarily break that symmetry with respect to inversion by bond stretches and rotations, and that would allow us to access some of these electronic transitions. So how does this relate to epsilon? Well, epsilon tells us whether we are following selection rules. So we have three ranges that we kind of focus on. Generally, if epsilon is lower than 10, that's a very, very weak transition. Those would be considered both spin and parity forbidden. So something that has an epsilon less than 10 might be a transition that involves a singlet to a triplet conversion, which is, again, is possible, but again, unlikely due to our spin selection rule. And it could be a parity forbidden transition, one in which we have the same symmetry with respect to inversion. So either a G to G type transition or a U to U type transition. Our second case that we could look at is if epsilon is between 10 and about 100, maybe slightly above 100. These transitions are generally spin allowed, so it would mean a singlet to a singlet type transition, while also being parity forbidden, so a G to G or U to U. This is the range that we look at for our metal transitions in our octahedral field. Again, if we follow that spin selection rule and we end up with a singlet going to a singlet or whatever that spin state might be, no matter what, it's going to be a parity forbidden transition for an octahedral complex when we look at that T2G to EG set. Lastly, if we see epsilon values that are greater than 100 or much, much greater than 100, these are both spin and parity allowed transitions. These are often called charge transfer states, or they fall into the realm of what we call charge transfer states because they regularly involve the d orbitals on the metal and electrons in those d orbitals transitioning into open pi star orbitals on your ligand. And so that actually moves the electrons from a orbital localized on your metal to orbitals that are localized on your ligands, hence the charge transfer name, right? So the metal looks like it's formally oxidized in this electronic transition where your ligands are reduced. So then this must be easy to measure, right? We were able to do it for titanium, our D1 case, but let's look at what happens as we move to a higher D count. So if we can rationalize our D1 metal, then it might make sense that we might expand this and look at a D2 case. So let's look at this vanadium complex here, right? So this would be a D2 metal center. So we would have two electrons inside our ligand field. And if we're looking specifically at our D to D transitions, it makes sense that we could measure this delta octahedral, right, at first glance just by looking at a ground state where we have both electrons in our T2G set, and an excited state where we actually have an electron promoted up into that EG set of orbitals. And this looks like it would be able to directly measure that value for delta octahedral. And yet, when you go in the lab, if you were going to measure this spectra, we actually see two absorbances that fall in the range of D to D electronic transitions. So it's not quite as simple when you move beyond a single D electron. We now start to see multiple absorbances. So how can we connect this data to a value for delta octahedral? And why is it that we're seeing two absorbances when we have this set of orbitals we're calling degenerate in T2G and a degenerate set of EG orbitals? Well, in order to understand this, we actually have to go all the way back to our derivation of our d orbitals themselves. So if we were going to look at a D3 metal center, you might look at these top electron configurations and say that they should be identical in energy because these are all d orbitals, and the derivation says that we should have 5 equivalent d orbitals. However, we need to remember that our orbital pictures and their relative energies are actually derived from a single electron system, right? So all of our orbitals are solutions to the Schrodinger equation that come from a single electron system, such as hydrogen. And so there's no way to accurately account for any electron-electron repulsions. So when we're actually looking at these orbitals, right, these 5 different d orbitals that we've solved for, there's a new thing we have to consider, which is called angular coupling. And that's the fact that electron repulsions are an important factor in thinking about electronic structure. We can't solve the wave function in order to get a picture that accurately accounts for these electron-electron repulsions, but they do exist, which means these states that look degenerate might not actually be degenerate. They might have slightly different energies. And so in order to do this, in order to dig into this a little bit deeper, we have to have a method of describing these different electronic states of our metal itself, right? So just looking at these 5d orbitals, if we're going to say these are different states, we need to describe them differently. And so here comes our good friend free ion term symbols. Now I'm going to get ahead of the game here and tell you our version of determining these free ion term symbols is kind of the cheater's approach to doing this, right? We're making some approximations to make our life easier. We are only trying to describe the ground state free ion term symbol for a metal. And this is something we're going to get some more practice with as we derive these different states. So for a D2 metal, right, we're going to follow the same 4-step process for any given D configuration. So the first thing we have to do is put those electrons into our d orbitals on the metal. So we have 2 electrons. That means that they can both be spin aligned in different d orbitals. We then would determine the total spin multiplicity, which in this case is actually not 2, as it's written on the slide. Our spin multiplicity is a 3. So our capital M sub S here should be a 3. Right, and not a 2, because I can do math. I promise I can do math. And so we have this capital M sub S, which is a 3. So this means this is a triplet state, right? It is a triplet state. Our third step is to maximize the angular momentum for this free ground, or this ground state of our free ion term symbol. So again, we go back to our quantum numbers from general chemistry and beyond, and we can see that for our d orbitals, right, we have values for our angular momentum from +2 down to -2 in single integer steps. So we can have +2, +1, 0, -1, and -2. In order to maximize this angular momentum, we would say that our electrons are in a +2 and a +1 orbital. So that means this capital M sub L has a value of 3. This is going to lead to a symbol, which is an F, and we're going to get to this in a second. And again, this spin multiplicity is a 3, not a 2. So we would call this a triplet state, not a doublet state. Right? Obviously, there's some editing that I'm going to do on this before I post it. So what do we do now that we have this? Again, we have this list of these symbols, right? And so if we're describing the ground state free ion term for vanadium here, right, that D2 metal, we would call this a triplet F ground state, right? It has that superscript 3 to describe the spin multiplicity. So where does F come from? Well, that symbol comes from this value of M sub L. Those of you who do computer science or maybe have some experience with Python in the past might be comfortable with the fact that we start counting at 0, because that's how it's done in Python. But this is our list in our table here. We can see that this follows the order of our orbitals that we are used to deriving. So S, P, D, and F. Values beyond that just go in alphabetical order. So we go F to G, and then H, and then I. And then you actually end up skipping J, but we will never get to that high of a value for our angular momentum. So now this describes again that electronic state of our free ion. But when we look at this vanadium complex, this is not in fact a free ion. This has water surrounding it. So as soon as it goes into an octahedral field, we start to see a difference in terms of the types of absorptions that we observe. These are actually well charted using what's called Tanabe-Sugano diagrams. And these are very busy and dense diagrams, what I'm about to show you. So this here is the Tanabe-Sugano diagram that describes all D2 metals. As delta octahedral increases, there's a great number of different electronic excited states that we can access. And so to break down the spectrum, we're going to get a lot of practice with this in class. But each one of these lines actually represents an electronic state. One of which is the ground state. We can see that this particular graph, right, all Tanabe-Sugano diagrams are corrected where the ground state falls at a y-axis value of 0. Blue lines actually represent our spin allowed transitions. So if you trace these lines all the way over to the margins, you would see that this red line, for example, has the label of a singlet state that is T1G. We don't need to dig so deeply into where these states come from other than pulling the labels off of the graph itself. We can see that a blue to blue transition, right, in the case of my ground state up to maybe this blue state, right, I see that this is a triplet state, and my ground state was again a triplet state. So blue to blue transitions are the main thing that we actually use Tanabe-Sugano diagrams for, because these represent our spin allowed transitions for our d orbitals. So we might notice that there's this other term that's in both our x and our y axis, this capital B. This is what's called the Ricard parameter, and this is an approximation for the covalency of the bonds in the metal complex. So this helps us to correct our spectra to get them onto a single kind of playing field. And we'll talk about how we use the Ricard parameter later. But for right now, what we can do, we can pull from this graph, is actually our two lowest energy transitions. So we can see that the first one is where we go from our ground state, again, this triplet T1G state, to our triplet T2G state, right? This is that lowest, or the lowest lying transition that we have is this blue arrow. And the second transition is actually, again, that triplet T1G state going to a different triplet T1G state. So it doesn't matter that the labels are the same. This has to do with the symmetry of the actual electronic state. What matters is that it is a spin-allowed transition. And we would expect to see potentially a third transition, right, to that triplet A2G state, right? In theory, we could calculate what this value would be, right? The energy required to get up here, and we'll get to that in a little while. But for right now, we can see we have these two different transitions. So if we go back to that absorbance spectra that we had, we can actually assign these two different peaks, right? The lower energy transition is that triplet T1G to the triplet T2G state. And the higher energy transition is the triplet T1G to the other triplet T1G state. So now, using the Tanabe-Sugano diagram, we can actually make some guesses about what it is we are seeing in our absorbance spectra, right? What is it that we are seeing when we look at a UV-Vis spectra? So what are we going to be doing next, right? Where do we go? Right now, we can derive the free ion term symbols. We're going to get practice with that. And we're going to start to look at these Tanabe-Sugano diagrams, but we don't really know how to use them yet. We're going to build into that, right? So some outlying questions that we're going to carry forward with us, right, is how can we actually use that UV-Vis data to determine an actual value for delta octahedral? Right? How can we turn that UV-Vis spectrum into an actual value for delta octahedral and the Ricard parameter, that value of B? And what does that tell us? And you might be wondering, well, how does this work for systems that have both high and low spin configurations? The short answer is that Tanabe-Sugano diagrams get very complicated very quickly. But we'll talk about how we can break those down so they aren't quite so intimidating. And lastly, what about a real spectrum, right? If we're given a spectrum that has lots of data on it, how can we connect that directly to the Tanabe-Sugano diagrams, right? So this is what we're going to be working on in class. This is where our problem set is going to take us, as well as into the other video that's coming later this week. All right, thank you. I will see you in class.